Hello there, folks. It is Mike, and I'm here with another solutions video. It's March 1st. We're in data management, and we are moving a little bit faster, and we got some more complicated stuff here. So I want to get right into it. I'm, as always, going to number each question, so you can fast forward to any point and look at the number of the question that you want help with. So again, this is video number 2. After March 1st and before the next video. So let's get into it. So the first question we have on tap is number 1. 3/4. Now this is times 7/8, but I do want to give some different fraction understandings, again, just so everyone is clear. If you're having trouble with this, know that the tops get multiplied and the bottoms get multiplied, and you keep them separate. So 3 times 7 is 21. 4 times 8 is 32. Make sure that bar is there. The answer is 21 over 32. The tops made this number, the bottoms made this number. If you're given a question like this, know that times is different than plus or minus. 3/4 plus 7/8 and 3/4 minus 7/8 are really radically different. Times and divide are separate. You go tops and bottoms. Here we need what's called a common denominator. A common denominator. Basically, the bottoms need to be the same. So when I'm doing this, I have to convert fractions into new fractions that are equivalent. 3/4, well, that's the same as 6/8. And if you can't see that, you're multiplying the top by 2 and you're multiplying the bottom by 2. Then you're going to add 7/8. Well, it turns out when you've got 6/8 plus 7/8, that's like 6 slices of an 8-piece pizza, plus 7 slices of an 8-piece pizza. You have 13 slices of an 8-piece pizza. The number of cuts never changes. So that stays the same. Same thing if you're subtracting 6/8 minus 7/8. You have minus 1/8. Negative 1 there for that. Again, keep in mind, multiplication different than addition and subtraction of fractions. Here, straight across, down here, common denominator for plus and minus. Hope that is helpful. The answer to question 1 in the problem set is that, 21 over 32. So let's keep going. Question 2. There's all sorts of power rules, and I need you to get to play with exponents. So remember, if I have 2 squared, that's the same thing as saying 2 times 2, which is 4. If I have 2 to the 3rd, it equals 2 times 2 times 2, and that equals 8. It does not equal 2 times 3 equals 6. That is wrong. It is 2 times 2 times 2. When in doubt, do it on your calculator so you don't mess it up. Now, I'm giving some more creative questions with powers, so I want to walk through a few different power rules. When you have, actually let's use x because you're used to that. When you have something x and you square it, and you add something else squared, you get 2x squared. Well, that's because when you add this thing and you add the same thing, you get 2 of those things. 2x squareds. You can't multiply those. You can't like bring them together in a different way when you add them. But when you multiply x squared times x squared, well, that actually equals x times x, right? That's x squared. then times x times x. Well, that just looks a lot like x to the fourth. X to the fourth is the same thing as x squared times x squared, so you add the exponents. So when you're multiplying two variables that are the same with exponents, you add those exponents. Now, what happens if I have an extra 2 or something in there? So if I add 2x squared times x squared, well, then I'd have a 2 out here. Well, then I'd also have a 2 in front, but I'd still have x to the fourth. So 2x to the fourth is there. This is all sort of preamble and will give you the ability to answer future questions, whether it's plus and you got to keep them separate and you bring them together by like the number of these items. If it's times, then you can bring the exponents together and add the exponents. And to give you a hint, here if I have x to the fifth and I put that in a bracket and I give you to the sixth there, it's not a very good 6. The way that's done when you take something and you exponent it on a bracket and put it all inside, it's x to the 30. How'd you do that? 5 times 6. So when you got brackets, you times the exponents. When you just have a times, you add the exponents. And when you have a plus sign, you just add the chunks if it's the same chunk. But, just to review, if you have, let's say, x to the third plus x squared, what does that equal? Well, it's not times, it's not a bracket, so we have one of these things and we have one of these things, but they're not the same. So you cannot simplify them. You can't bring those together. And that is a really important fact. X to the third plus x squared just equals the same thing. You cannot simplify that anymore. Whereas x squared plus x squared is two of these things because I have two of the exact same thing. Now those are the power rules, and so let's actually get into applying these in practice. Now the power rules also count for division. So when I have 2 to the sixth, well, we know that's going to be 2 times 2 times 2 times 2 times 2 times 2. And we're going to times. So that means it's not in the addition, right? If it was add, then we'd have to say how many of these things and how many of these things. But because it's times, if it was the same, we can use the exponents and kind of bring them together. But let's see what we have in that second one. 1 over 2 to the sixth. Well, that 1 over 2 to the sixth is kind of like times 1 over 2 times 2 times 2 times 2 times 2 times 2. 6 of them. Now, any number over 1 is just equivalent to itself. Now that looks an awful lot like a fraction. Here's a fraction, here's a fraction. We're going to multiply them both. We're going to bring them together. And then we've got 6 2's up here. And we have 6 2's on the bottom. But there's this rule that when you've got the same thing on the top and bottom, you can cancel it out. So on any fraction, when it's an isolated fraction and everything is multiplied together, then you can cancel those. You can cancel those, cancel, 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 cancel. So we're actually just left with 1 over 1, which is 1. So what I did here whether I said, okay, put a bunch of 2's on top, put a bunch of 2's on the bottom, multiply them together, and then see that they cancel. We're going to play around with power rules and a few other things here and exponents. So keep in mind that the top numbers cancel out with the bottom numbers when they're all multiplied together. So the answer to question 2 there is 1. In the future, you're going to need these kinds of rules to make other questions work. So let's erase that. We'll go into question 3. So question 3 you can do in a couple different ways, but the easiest one is with your calc. You can use your calculator. 5% times 0.15 times 1/8. Really what I'm testing you with here is your ability to convert these different things into something that's usable. Your calculator always speaks in decimals, this language. So how do we get from percent to decimal? Well, 50% is the same thing as 0.5. 5% is the same thing as 0.05. 1% is the same thing as 0.01. So hopefully you can start to see that pattern. So 5% here we can replace with 0.05. Well, and 0.15 is just a decimal. Now what about a fraction? How do we convert a fraction into decimal? And here's a trick for you. You take the top and you push the divide symbol and then you enter the bottom. So if I pull out my calculator and I say I have 1 and I divide by 8, I get 0.125. So 0.125 is what spits out, and now that has given me 1/8 in decimal. So if that was 2/8, I would have done 2 divided by 8. If that was 3/8, then I would have done 3 divided by 8. That's how you convert fractions to decimals. So now, to solve this, I just go and calculate these. 0.05 times 0.15 times 0.125 equals 0.009, and actually my calculator is rounding there. So the answer here is 0.0009, but I just need to get the rest of the decimals there. 9375. So apologies there, I had to figure out a way to show the extra digits on my calculator. 0.000935 is the answer. Convert them all to decimal. Easiest way to do those. So that is question 3. Now, question 4 is figuring out the probability of occurrences. I'm going to try to use coins and flipping coins because it is the easiest. So for question 4, we've got flipping of heads or tails. Don't forget, when events are disconnected, we can draw a probability tree when they're independent from one another. So on flip 1, the outcome can be heads or tails. Now we're saying that 50%, or 1/2 of the time it's tails, or 1/2 of the time it's heads. And we can do that again. We can say flip 2, but flip 2 can happen after either a head or a tail. So we want to write that out, and then again, we can have a head or a tail. We can have a head or a tail. So each of these is 1/2. each of these is 1/2 of a probability. And you can see that on the flip one, the probability of it landing tails is 1/2, but the probability of it landing tails and then tails again and getting to this outcome here of 2 tails are these 2 probabilities multiplied together. So let me be clear. This probability comes in, this probability comes in, you multiply them together here, and you get 1/4, which is the probability of having 2 tails in a row. Now, the actual question is flipping 4 heads in a row. So we're not looking at that side. We're looking at heads here, then another flip 3 to give us a head, and then another flip 4 to give us another head there. So we got 1/2 times 1/2. Well, and the probability is 1/2 again and 1/2 again. So what I can really write that as is 1/4, or I'm sorry, 1/2 to the 4th, or 1/2 times 1/2 times 1/2 times 1/2. What? So 4 heads in a row is 2, 4, 8, 16. 1 in 16 chance, 1/16 that you're going to get 4 heads in a row. Now there's ways to ask questions in more interesting ways. To say, what's the probability that I get a tail, and then a head or a tail, and then only a tail and then a head. And so you heard in my language that you can have an extra little piece or structure to say maybe flip 2 doesn't matter. Maybe flip 2, whatever. It's like one or the other. Flip 2 doesn't matter, but flip 1, 3, and 4 matter. In which case, really when you think about it, if this doesn't matter, you just multiply by 1. And so we can start to piece through, and we want to count the number of options at the end. If you did this tree and did 2 and then 2 and then 2 and then 2, you'd actually have 16 outcomes at the end. And we only want one of those 16. But sometimes the question will be asked in a way that you want more than one outcome. For example, I could ask, what's the probability of getting a head and then 2 opposite heads or tails in a row? So you want to have, let's say, what's the probability of a head, then a tail plus a head, or a head plus a tail? But the head plus head or tail plus tail, well, those don't count. That's not what I want. I want these things. So now I've said 1/2, and then of all the possible outcomes, you can count them up. And so there's 1/2 here and 1/2 there, or 1/2 there, then 1/2 there. And so the probability of this is 1/8, and the probability of this is 1/8. And then you have to add those together. So 1/8 plus 1/8, 1/8 plus 1/8 is 2/8 or 1/4. So in this other scenario, again, ignore this if you're just focusing on the question 4 as its simplest form. But later on, I'm going to ask question 4s that get more complicated that include more options. So once you include more options, you got to start thinking about, okay, out of the total number of outcomes, how many are we actually talking about? And in this particular question, we're talking about 2 potential outcomes. So I hope that helps. Probability trees can get quite large quite quickly, so hopefully you don't have to draw them too big. So that is question 4. Question 5. So, question 5, we talked about a normal distribution. And a normal distribution is a bell curve. It looks something like this. It means this is the most likely thing to happen. So let's say how tall people are. We give an example where the average male in America is 5'10". And there is a 3-inch significant or standard deviation. And so 6'1" is the next here, and 5'10" or 5'7" is the next one here. The normal distribution has some very particular properties. There is a mean, there is a middle. And so in the question here, we've been given x bar, which is said x bar equals the mean. You've been calculating that already, right? Remember just how to calculate the average. To calculate the average of a data set, it's you add up all the numbers and then you divide by the number of numbers. But in this case, we've said it's 10. Then we've got this standard deviation piece, which is also sigma, or standard deviation. The standard deviation here is equal to 2. So with a mean of 10 and a standard deviation of 2, we can actually draw this out with the intervals going out. So I'm going to draw this bigger on the sheet of paper just so it's really clear. There are other videos that I've posted about this. If you're having a hard time, please do go back and watch those videos. So to answer question 5, you're going to have to draw a graph, and it's always going to look like this. The mean on your graph is going to be 10 because we were given x bar. This is x bar, the height of the graph. Or this is the value of the highest point on the graph. Then sigma, or standard deviation, is out here, and 12, well, that I would label as sigma 1, or as the standard deviation of 1 unit out. On the other side, I would say this is 8, because this is minus 1 standard deviation. Now if we go another one out to here, to 6, we're going 2 sigmas out, and in the negative, and on this side we're going to 14, which is sigma 2. This is really all that you have to draw at this point. You can do a third, but I want to make sure that everyone gets comfortable with the idea that your standard distribution, given the normal distribution, your standard deviation, is a certain value outside of that mean in both directions. And in this way it's negative, in this way it's positive. So this kind of graph would get you perfect marks. You want to acknowledge this is the mean, or x bar. You want to acknowledge that every step out of sigma, of the standard deviation, is 2, and you've written that in numbers here. And every step, the probability of it occurring goes down. So just to give a quick example, the probability of something really bad happening to you is quite low. The probability of something really, really good happening to you is quite low. But every day is going to be pretty okay, or pretty much the same as yesterday. That's the average. So you can expect the average, but sometimes something really bad happens and sometimes something really good happens. That's just kind of how life works. This is now us calculating those out. And just for reference, this is 34% of people. This is 34% of people. And then 68 to 95 is 27. So this is about 13% of people. This is about 13% of people. And so all in total, you know, from here to here, 95% of people exist within 2, and 68% of people exist within 1 standard deviation of the mean. Looking at height of people, looking at number of birds that you're counting, looking at number of baskets scored, 68% of people generally occur within 1 standard deviation, 95 within 2, and 99 within 3, just as an FYI. So you don't need these percentages yet. I'm going to ask for them later, but just know that they exist for when I include them. So that's question 5. We'll draw that normal distribution graphs. Question 6. Most of you are going to say, what the heck is 5 exclamation mark? And it is not an excited 5. This exclamation mark is a very particular mathematical concept. It says, when you say a number and exclamation mark, you want to take that number and then take every number smaller than it and multiply them all together. So what did I do? When I see this exclamation mark, it's called factorial. So I would say 5 factorial. 5 factorial means 5 times 4 times 3 times 2 times 1. This is 20, this is 60, this is 120. The answer here is 120. You'll see quickly factorials get very large. But we have to work with them because there's certain math, especially in the next couple of questions, that are going to be very essential. So factorial, or exclamation mark, means take every number smaller down to 1, multiply them through, and what do you get? So, take a break here for a sec. All right. So that is question 6, factorials. Question 7. Now, question 7, you're going to see it and you're going to be like, what the heck are you talking about, Mike? 5p2. Well, what this means is a permutation. Permutation. Sometimes you have 5 people. We're going to make them stars. We have 5 stars here. And you need to pick 2 of those. But the order matters here. So in this one, I'm going to pick this one as 1, and then I'm going to pick this one as 2. So that's one option. Now, in another choice, I could pick like this one as 1 and this one as 2. I could also flip those, right? Because order doesn't matter here. So I could say, if that was 1 and that was 2, now that's 1 and that's 2. So those are each counted. Sometimes I really need to know how many options there are that exist. That's what P and C are doing. Questions 7 and 8 are telling us how many possibilities can we pick or choose. That is a terrible cheese. Choose. Choose. How many possibilities can we pick or choose from here? And they're different in that there's a different formula that you need to remember for both. Now, in P, we're dealing with permutations. So, first things first, we're doing 5p2. To give you the formula, 5p2 equals n factorial over n minus r factorial. What the heck does that mean? Well, if you don't like formulas, you can ignore that, but you should know that that exists. So, for this question, I take 5 and I put it down on top. I take the first number and I call it its n, and I say 5 factorial. Then I take that same number and I put it down here, and so I say 5 minus, then I take this second number and I plug it in there. So I say 5 minus 2 factorial. So what does this actually mean? So this first number gets used twice. It gets used in the top and the bottom. The second number only gets used in the bottom. So now I've got 5 factorial, which is 5 times 4 times 3 times 2 times 1. And on the bottom, I have to do what's inside the brackets first. So I do 5 minus 2, which is just 3 factorial. 3 factorial. But 3 factorial actually equals 3 times 2 times 1. So now this would be my answer, except the tops and the bottoms cancel. Because when everything's multiplied together, and there's numbers on the top that are the same as the numbers on the bottom, they cancel. The 2's cancel, the 1's cancel. And I'm left with only numbers on the top, 5 times 4. 5p2, after I do all of this math, is 20. 5 times 4. Just to review, this is the formula. I take the first number in front of p, I factorial it on the top, I divide it by the first number minus the second number. And then I factorial that. I cancel some stuff out. There will always be stuff to cancel. And whatever I'm left with, whatever is up on here and whatever is down below, I then divide or multiply and I get a particular number. There are 20 ways in which I can pick 2 things from 5 things. That's the answer to this question here. Now, to switch it up a little bit, I'm going to erase most of this here, but I'm going to say that for question 8, and we got question 8 here. So we got question 8. We're doing 5 choose 2. Now you might not think that's very important, but 5 choose 2 are combinations. And the main thing about combinations is about order. And so whether or not the order matters is a really big deal. So if order doesn't matter, it's going to drop the number of possible combinations. Now, I haven't changed this formula because it doesn't change that much, but when I change C, when I change from a P to a C, I have to add one thing here. And it's going to reduce what my final numbers are. And that actually looks like this. R factorial on the bottom. So I now use this second number and factorial it on the bottom to reduce. Whenever you divide by something, you reduce the total number, because the number of combinations, when order doesn't matter, decreases. So we want to drive this whole number down. So let's do this again. We're going to take 5. We're going to put 5 factorial in the top for n, that first number. Then we're going to take and I'm actually going to flip this. I'm going to put the r factorial afterwards. So I'm going to say r factorial there. So from the 5 goes also into here. So 5 minus, same thing, 2 factorial. The 2 we got from up here, and then times 2 factorial on the bottom. So the 2 comes in twice, once there and once there. In combinations, when we choose, we use both numbers twice. 2 5s here, 2 2s here. So now we do the math, and we say, what does that equal? Well, that's 5 times 4 times 3 times 2 times 1 over, well, what do we have? 5 minus 2 is 3 factorial. 3 factorial is 3 times 2 times 1. And then we've got this r factorial, or 2 factorial here. So that's 2 times 1. And don't forget, those are all multiplied. So how does this play? Well, now we have to cancel, because these numbers are the same on top. These numbers are the same. This 3 is the same as this 3. And then we're left with 5 times 4, but this 2 still hasn't been factored in. 1 doesn't really matter, so we can get rid of that. So we have 5 times 4 over 2 is still down here. So that's just 20 divided by 2, or 10. 5C2 had a little bit more trouble here, a little bit more going on with this R, or the second number exclamation mark. And so with that extra 2 that carried through, instead of 5P2, which was 20, 5C2 equals 10. That's how many combinations there are when you have 5 things and you want to choose 2 of them. So the final answer you should get here is 10. Again, P and C are so similar except for this R factorial on the bottom. And then the math, you just got to divide through. So that's question 8. And then we've got a data set. So I want to do 9 first, which is mean. So in any data set, I add, first thing I do is I add all the numbers. Then, second step, I divide by the number of numbers. So in the data set that I was given, 5, 6, 7, 8, 9. Now I know some shorthand, and the more that you do these, the more that you will be able to do these really quickly. But let's just do these together. So this is 11, that's 20, that's 27, that is 35. So when I add those all together, I get 35. Now I need to divide by the number of numbers, which is 5. There's 5 distinct pieces of data. 35 divided by 5 is 7. This doesn't happen all the time, but this middle number is here. And so the median and the mean are the same, which doesn't happen all the time, but there's a reason why I gave you this, because then all the other numbers kind of play well. So the mean, which is also known as x bar, which you can get used to here, of this data set is 7. Cool. So that's the mean. Now, we have to do some fancy stuff to get the standard deviation. And this is one of the most important skills that you can have in data management. For question 10, standard deviation. Standard deviation is a measure of what is the spread out of any data set. And when I look at 5, 6, 7, 8, 9, there's a little bit of a spread there, but it's pretty tight. So I should expect to get a pretty narrow or small standard deviation. Now, how do I calculate the standard deviation? Well, I got to remember that my x bar, my mean, was 7. So first things first, I need to write out all my data, 5, 6, 7, 8, 9. Then I need to write out x bar, which is 7, 7, 7, 7, and 7. Then I'm going to have the number minus x bar. So 5 minus 7 equals negative 2. 6 minus 7 is minus 1. 7 minus 7 is 0. 8 minus 7 is 1. And 9 minus 7 is 2. So I have taken these numbers and subtracted the mean. Now, you want to take this thing and you want to x minus x bar, and you want to square it. So negative 2 squared, a negative times a negative is a positive. So negative 2 times negative 2 is positive 4. Negative 1 times negative 1 is 1. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. So now, what do? Well, we basically take the average, and I'm just going to say average, of all of these numbers. So the average of all of these numbers is going to be 4 plus 1 plus 0 plus 1 plus 4, all divided by 5. Now, you're noticing I already did an average. And so standard deviation is literally just a second average of the differences. It's saying there is a difference. And what is the standard? Well, it's the average. The average difference. The average difference is the standard deviation. You're just taking the average of the differences squared. Now, 4 plus 1 is 5, plus 0 is 5, plus 1 is 6, plus 4 is 10. So I have 10 over 5, which is 2. But am I done? No. The last step always square root. That is a square root. So I need to take my answer and I need to square root it. So the standard deviation of this set of data, 5, 6, 7, 8, 9, is going to be the square root of 2, which on my calculator is 1.41. So this is the answer down here. 1.41 is the standard deviation. I can also write that as sigma. Sigma equals 1.41. So sigma equals 1.41. I took the data. I found the mean. I subtracted the data from the mean. I squared that difference. I added it all up and took the average of those differences. Then I square rooted that, and I'm left with a standard deviation of 1.41. Now, I could then draw a bell curve of this. I could have an average number of 7 with a standard distribution going out of 1.41 in those increments as we go out on the chart. I hope this is helpful. It should be. If you have questions, obviously ask me. I also wanted to just talk about what this sigma of 1.41 is and what it means. So there's a few things that sigma being 1.41 means? First of all, it's quite small. And it's small relative to the numbers, which is nice too. So it's maybe 10% of that number. I mean, it's like, 20, 25% of that number. So it's like not super small. If this was how many people were dying from COVID in our classroom, then that would not be a good number or a standard deviation to have. But with this graph, and when you're drawing it, and you've got a standard, or this x bar is 7, then one standard deviation over is 8.41. And one standard deviation over here is going to be 5.59. That means, because I know the shape of this curve, I know that 68% of all data should land between those two numbers. And I know that if you go one more standard deviation out, 95% of all numbers should be within those confidence intervals. So if I gave you one more piece of data, you would guess that 95% accuracy, if you go one more confidence interval out, what is that? That's about, let's call it 4. It's 4 and change. And then let's call this 9.82. 95% odds. The next number that comes out is between 4 and 9.82. But there's a 68% chance that the number is between 5.59 and 8.41. So given the standard deviation and the mean and the data set, you can start to know a lot about how to chunk this. You can say that 50% of data should be less than 7%, or 7, and 50% should be more. There's all sorts of conclusions that we can start thinking about there. So, wanted to leave you with that. Hope this is helpful. Thanks very much for listening.